So now you know how we found the Ka values of acids. And again, those Kas are given in this reference chart. The next thing you can do now is, since you know the Ka, you can get the pH of any acid, whether it be strong or weak. To get the pH of a strong acid, all you have to do is know that you have 100% dissociation, 0.01 molar, 0.01 molar, 0.01 molar, take the negative log of 0.01 molar. If you have a weak acid, you don't know how much comes apart, but because you know Ka, you can calculate for it. Okay, so this is 0.01, you don't know how much H plus and F minus you'll have. So to do that, all we have to do is set up an icebox. Okay, so how do you know the pH of a substance of a weak acid if you know the Ka? Okay, if you know the Ka and you know how much you put in there, the concentration of a weak acid, you can get the pH at equilibrium. All you have to do is set up an icebox. In this problem, it says calculate the pH of 0.3 molar of acetic acid. So you have 0.30 molar of this, right? At 25 degrees. And these Kas are at a certain temperature, and they are at 25 degrees Celsius. Okay? So now, if this is a weak acid, this is not going to be 0.30, and this is not going to be 0.30. You don't know what it's going to be, okay? So it's a question mark. So you can't take the pH really easily. But you have to look up for the Ka to find out what the pH is. So the Ka for acetic acid is written here. It's 1.8 E negative 5. So I'm going to write 1.8 E negative 5. That's very important. That's Ka. And the formula is H plus times C2H3O2 minus over HC2H3O2. Okay, so you can already tell that all you have to do is plug in this number into the Ka, set up the icebox, and solve for these at equilibrium. So let's do that. So we have the equation here. Initially, I have 0.30. I don't know, I have 0 of these in the beginning because I didn't put any of them in the beaker, just this in the beaker. It's going to be minus x plus x plus x, because that's the change. At equilibrium, it's going to be x, and 0.30 minus x. Plugging that in here, Ka, which is 1.8 E negative 5, you plugging into the equilibrium expression, which is this, okay? 1.8 E negative 5, H plus is x. Acetate ion is also x, divided by 0.30 minus x. And all you have to do here is solve for x. Okay, so you're going to get 1.8. Okay, so first, we are going to see that this number right here, the Ka, is really small. Remember, e to the negative 4 or smaller, which tells us that x is really, really small, and we're going to use that assumption to make this equal to 0. We're going to call it negligible, because a very little amount of it breaks apart because of the small Ka value. Okay, if it's less than E negative 4, you can do this assumption. So taking this out as 0, you can just solve for x. Okay, so x is equal to 0.0023, which is equal to, this is equal to the molarity of the H plus. And if you wanted to get the pH, and the question says calculate the pH, now that you know the H plus, you're just going to do pH equals negative log of the H plus, which is 0.0023, which is equal to pH of 2.63. So what that means is if you have some acetic acid or vinegar on the counter and you use the 0.30 molar, this will be the pH of that solution. Okay? Here we are assuming that X will be very small, less than 5% ionization when compared to 0.30, which is the original. So therefore, we can be ignored. X can be ignored. To make sure there's less than 5% dissociation, we have to check it, okay? To calculate the percent ionization, how much H plus did we get? 0.0023. That's how much break apart. Percent ionization is equal to 0.0023. How much was it originally? It was 0.30 originally. Times 100. So the percent ionization is equal to 0.77%. So because it is less than 5%, it's less than 5%, we can use the assumption that we can get rid of X and call it negligible. Okay? So now, let's compare two acids. If you have a 0.3 molar of HCl, all you have to do is, since HCl is strong, H plus and Cl minus, 0.30 of this will give you 0.30 of this, will give you 0.30 of this. So to get the pH of this, just type in 0.30 and you can get the pH. The pH of a strong acid is 0.52. This is 0.3 molar HCl. If you take a 0.3 molar acetic acid, notice they're the same concentration. You got 2.64 right here. 2.63, 2.64, whatever. Okay? This is the pH of a strong acid, and this is the pH of the weak acid. And notice they have the same molarity. Obviously, the strong acid is more acidic because it dissociates more than the weak acid. Okay, 16.12. Sample exercise. Calculate the pH of 0.2 molar solution of HCN. Okay, please pause the video and try this yourself. Okay, so first I'm going to write the equation. HCN becomes H plus and Cn minus. This is a 0.2 molar of this, and they didn't add any of these two, so I can just 0, 0. And you know that HCN is not a strong acid, so it can't just be 0.2, 0.2, 0.2. So you have to set up an icebox. Minus X plus X plus X. XX. So 0.2 minus X. Okay, so now you have to find the Ka for weak acids. You look at this chart, and you're looking for HCN, hydrocyanic acid. Right here, hydrocyanic acid is 4.9 E negative 10. That's a really, really weak acid, isn't it? 4.9 E negative 10. So 4.9 E negative 10. Okay, so Ka is equal to H plus times Cn minus over HCN. Ka is 4.9 E negative 10 is equal to, this is x and x, so x squared. This is x, okay? So I just wrote x squared divided by, call this negligible because it's really small, hardly there. 0.20, solve for x is going to be equal to 9.9 E negative 6. That's going to be the molarity of H plus. It's also the molarity of HCN. Note that because they're the same number. If you want the pH, just log that. pH is equal to negative log of the H plus value, which is 9.9 E negative 6. So the pH of this is pH 5. And I have 2 sig figs here. So I'm going to write 5.00 with 2 sig figs. Okay. Since I use I assume this is 0, I have to check the percent ionization. So I'm going to start with how much came apart, which is x, which is right here, 9.9 e negative 6 divided by, originally is 0.20. 0.20 times 100, which is 0.0050%. And that is way less than 5%, so therefore my assumption here that this is 0 is fine.